And I'm happy to present for the international webinar series on environmental engineering. And as you mentioned, the title of my presentation is Exploring the Interactions of Temperature, Pore Water Pressure, and Pore Fluid Flow in Soil Media. By growing interest in applications of the energy structures and harvesting geothermal energy and as one of the renewable sources of energy, and this is a growing interest to utilizing this using energy walls, the energy piles, geothermal piles. So we are changing the ground temperatures and soil temperatures. To carefully design and to better accommodate these energy structures, we have to carefully understand the soil behaviors under non-isothermal loading or the effects of thermal loading on soil behavior. Apart from the energy geostructures, also by embedding the evasive disposals in the ground, we are changing the soil temperatures. And either the seasonal variation of temperature around the world. Also, at different countries, you'll have different delta T that happens in the summer and winter, and it can be as high as 50 degrees or more when comparing the temperature variations in the ambient. So that will affect the shallow surface soils temperature changes. So that's the scope or focus of our research to understand the effects of temperature on soil behavior. When we look at the temperature's effects on the soil behavior, we can see that, okay, temperature will change the hydraulic conductivity of the soil. And the first thing that comes to our mind, yes, because of the groundwater or the water properties are highly temperature dependent, the viscosity, for example. So thus we will expect that to see the different changes in hydraulic conductivity. But how about the intrinsic permeability, or are we going to see any changes in the intrinsic permeability of the soil medium because of this thermal loading? And also the S strengths, of course, the temperature, we can see, can the temperature changes anything on the mechanical side, like as the changing the volumetric changes? Can it be happen because of temperature? And we call this a thermal consolidation. And all in all, if we look at the overall perspective, that temperature can change the whole systems, and which is highly interacted, which the hydraulic system and mechanical system. So thus we have to provide a good insight, and we have to develop a fully coupled thermo-hydro-mechanical modeling or thermo-hydro-mechanical chemical for different cases. Let me see, so the thermo-hydro-mechanical modeling, the coupled thermo-hydro-mechanical modeling, we have three, I would say, separate physics: hydraulic, thermal, and mechanic, which highly interacted and interact each others on this thermo-hydro-mechanical response. For example, hydraulic loading, when we have any groundwater flow or any flow in the soil medium, that makes the heat convection and will change the soil thermal response. And on the other side, temperature itself can make some pore water pressure, induce pore water pressure, and so that's the interaction. On the other side, thermal and mechanical, thermal can or may increase some changes the volumetric, and then if we have any porosity changes or mechanical load, if we do have any changes in the soil volumetric, will also affect the thermal properties of the soils. And hydraulic and mechanical, same. So this is highly interacted to each other, and we need a fully coupled system to better captures the thermo-hydro-mechanical response of the soil. The core of a study in this presentation that I am focusing on is on the saturated soil. And we are looking for the temperature increments and the response of the soil under the term because of this delta T or the thermal loading. But first, we need to classify this into two big categories, as a low permeable soil and high permeable soil. And low permeable soil is what we know as a fine soil, like as a silt or clay. And high permeable soil, as we know, is a coarse soil, like as a gravel or sand. So the reason I divide this, you will see the results, and you will see the reason why I make this two categories. In high permeable soil, what is happening is that when we have a temperature increment, I'll show you that later, that the temperature can make a groundwater flow even in under hydrostatic condition, that we call it as a thermally induced water flow or thermally induced pore water flow. And this flow can further change the temperature because of this heat convection mechanism. In low permeable soil, On the other side, because the permeability is very low, we won't see this significant, or the effects of this thermally poor water flow is negligible. But on the other side, because of low permeable, and if we do have a thermal loading, we will have some thermal pressurization or thermally induced pore water pressure. And then by generation and dissipation of this pore water pressure, we'll have some thermal consolidation or thermal volumetric changes. During this presentation, I will go through different research tasks that we performed to answer our research questions. And one of the tasks we did was experimental side to understand the changes in permeability or hydraulic conductivity of the soils with, of course, with the thermal loading. And then we did some thermal volumetric changes to understand the thermal consolidation of the clays. And after the first part, which is going to about the experimental part, I'll focus on the numerical side of our research, which is modeling the hydrothermal. I'll first start with the hydrothermal, which is called as a coupled heat and pore water flow, to show you that how this temperature increment can make the thermal induced pore water flow. And then we have the coupled THM modeling to capture thermal response, hydraulic response, and mechanical response, and the interactions of these three mechanisms. So first, I'm going to focus on the experimental research that we did, and by that, I'll focus on permeability test. To understand the effects of temperature on the permeability or hydraulic conductivity of the soil, we modified our triaxial cell, and we used a temperature control thermometer cell. It has a fluid, comparing to the regular triaxial cell, the system has a constant water bath and also circulation fluid temperature, circulated controlled fluid temperatures inside the cell that we can control and change the temperature of the soil specimen. We did some calibration, and then we have the device ready to do some permeability testing. So we pass the water, and then we use this to understand how much would be the changes in hydraulic conductivity under non-isothermal loading. And we did this test for both Ottawa sand and kaolin clay, but today I'm going to focus more on the Ottawa sand and soil characteristics or geotechnical and thermal properties of the sand that we did use. I provided here. And what we did is that we have a specimen, we pass the water, and we increase to do it regular permeability test. But the difference is here is that we are increasing the temperature of the specimen to a target temperature, and we started from room temperatures from 20 and 23, and then we increase it all the way to the 80 degrees centigrade. And at each step, we measure the permeability or hydraulic conductivity at least 3 times, and then to make sure that the repeatability of the testing. And what we see here is that I'm showing the hydraulic conductivity versus temperature at different temperature response or at different thermal loading steps. By increasing temperature, we do see that the hydraulic conductivity of the soil increases. We perform this test under different confinement, and as we can see here, this heating load increases the hydraulic conductivity by 34%. But this comes to the questions, this brings a question, how much of this is because of the changes in water or water properties because of the changes in viscosity and unit weight of the water, basic density of the water with temperature, and how much is intrinsic permeability? To do that, we did measures the changes in the viscosity of the used water in this test at different temperature. And by the known equation, all of you know about the relation between the intrinsic permeability and the hydraulic conductivity. We calculated the intrinsic permeability of the soil at each of those loading thermal steps. And interestingly, we see that this intrinsic permeability versus temperature, as we can see, by increasing temperature from 20 degree to 80 degree at different thermal steps, the intrinsic permeability reduces. This intrinsic permeability reduced by 44% by heating, and as the Ottawa sand is a sandy soil. So this will tell us that not only hydraulic conductivity is a temperature dependent, but also the intrinsic properties of the soil, such as the the absolute permeability is changing with the soil temperature. And I have these two side by side, but this is for different confinement. So we repeated this for different confinement, and for this confinement or test 5, and I'm showing the results. As again, we do see an increase in the hydraulic conductivity with temperature, almost again same as 40%, and then again same as 40%. We see same as before with the lower confinement, we do see a drop in intrinsic permeability of the soil. So when we do see this intrinsic permeability drop, there would be two reasons for that. We can say is that soil rearrangement happening, and then the tortuosity or the pathway of the water can be changed. In addition, might be there is a volumetric changes in the soil, that we are compacting the soil further, and because of the lowering the void ratio or the reducing the voids, we will see this lower intrinsic permeability with thermal loading. To calculate the volumetric changes for this specific soil, for sandy soil, we measured during the test, we measured the amount of water expelled through the specimen or adsorbed through the specimen by heating and cooling load. And then by comparing with the expected changes in the volume, we know the thermal expansion coefficient for water, thermal expansion coefficient of solid grains. And by knowing those exact values, we can calculate the total volumetric changes of the soil. And we did check the void ratio changes on volumetric changes of the soil with temperature, and we did observe that there is a drop in the void ratio with temperature, and we are providing the void ratio changes with temperature. So basically what it tells us is that thermal loading makes the rearrangement and makes some reduction in the void ratio, and that's why of the reason that we see a lower intrinsic permeability at higher thermal loading. Next, I would like to discuss about the experiment that we did on kaolin clay, which is more focused on thermal volumetric changes in clay, or we call it as a thermal consolidation. All of you know about the regular consolidation. It's happening because of generation of the pore water pressure and dissipation of the pore water pressure that is happening because of the mechanical loading. Now our loading is thermal load, and because of this thermal loading in clay specifically, we'll have pore water pressure induced, and then this dissipation, we will expect it to see this time-dependent thermal consolidation or thermal volumetric changes. To do that, since we are going to go 3 cyclic heating cooling cycles, we have to change that to aluminum cells. So it's aluminum cells, and we repeated the test for several heating cooling cycles. We did use our temperature control triaxial cell, and we did use this constant rate the CRS, basically CRS insert in the triaxial system. Because we are dealing with the thermal loading, before any experiment, we have to calibrate the system, same as before. For this specific device and this testing, we're considering the room temperature, cell temperature, uplift pressure, and mashing deflection that's happening because of, for example, increasing the heating load. We heat the up with the dummy samples, and then we track the displacement measured at the triaxial system. And then we calibrated it, and this dash line, as you can see, this solid dash line is a calibrated system. So it's showing that when there's a dummy samples, there's almost zero displacement. Then we did start testing, and this calibration is applied to every test that we did afterwards. One of the tests I am presenting here is the void ratio variation versus time. So it's same as the regular consolidation, which we observe the void ratio variations. We have void ratio changes, but our sources of the loading is thermal loading. And thermal loading, as you can see in the left figure, this is versus days. This is one of the tests that it took 24 days. We have the heating load. Initially, we started with the ambient temperature or room temperature. Then we heated it to 35 degrees in one step, kept it for a day, and then heated for a second heating a step, kept it for 1 day, another heating a step, kept it for 1 day. Then we cool it down step by step until we reach to the room temperature. And then we further cool the system to measure, to explore the cooling load system. And then, so we reached to almost 10. 8 degree, and then we started to heat back for a second or reheating. So please keep your questions at the end. So we have this heating load, and we further heated to the same temperature that we initially had for 60 degree, and we further heated this to 80 degrees centigrade, and then we cool it back. So this is 2 heating cooling cycles that we have in this model, and the red curve shows these volumetric changes or void ratio changes with heating load. And we clearly see there's a drop or changes in the void ratio with heating load. And to better show that, I'm presenting this void ratio changes versus logarithmic temperature instead of time now. And we have heating load, cooling, reheating, and then cooling back. So almost a figure similar to the consolidation we expected as a void ratio versus log of the sigma prime. Effective stress. Now we have it versus the log of temperature. So it's a semi-log axis. And we found the slopes of this as a heating load or compression because of the heating, and this swelling or this because of the cooling indexes. So it's almost, we observed very higher sloped during the heating, but lower as a cooling load, which is almost same as what we do see in regular consolidation. We repeated this test for several times, and by this time also at this step we changes the heating load. We kept our at each thermal load, I said that we kept 1 day. Now we were applying different heating rate for staying at 12 hours up to 1 hour, and then 12 hours up to 1 day, and also with different heating rate instead of 3 times or 4 time heating. So we expected different. We want to see if that changes the results. So we did heat it 2-step, 3-step, or staying 12 hours in each thermal step. And we observed that 12 hours was enough, that almost most of the thermally induced pore water pressure was dissipated within the 12 hours at each thermal step. And in each of these tests, we saw almost similar behavior by thermal volumetric changes, or we call it as a thermal reduction, the volumetric reduction with thermal loading, with almost the same slope. But those are for normally consolidated clay. We wanted to explore what happened if we do have an over-consolidated soil. We knew that over-consolidated soil under mechanical loading also show different behavior. So that's why we performed very highly over-consolidated sample with the OCR of 6.5. This is void ratio with, again, the log of temperature. And this time, instead of the contraction behavior, we observe the dilation behavior. And by heating, we do see this thermal expansion or dilation. And then cooling, reheating almost follow the same line. And then we further heat the soil up to a higher degree temperature. So the reverse behavior we observe as we expected in the over-consolidated soil. So if we see normal consolidated soil, we do see contraction. For highly over-consolidated soil, we do see a dilation. At some point with the slightly over-consolidated, we would expect then that would be a switch. So we did some testing, and we found out that the OCR of the 1.6 or slightly over-consolidated samples, we observed that temperature doesn't have any effects on the void ratio changes, or basically there's no or negligible thermal volumetric changes at the OCR of 1.6 at this confinement. And we observed here is that heating, cooling, basically heating, cooling, reheating, and then again we cool the system, no volumetric changes observed. If I want to draw this and the volume temperature versus the volumetric strain, I am presenting the results of the changes in the volumetric or thermal volumetric changes in the soil, in the kaolin clay, by heating load and at different over-consolidated ratios. So this red one here is over-consolidated of 1.6 or slightly over-consolidated, the solid red. When we have a normally consolidated soil, we observe the thermal positive is thermal contraction. So we observe the contraction. But for highly overconsolidated soil, this blue dash line with the hollow square, this is going to be the highly overconsolidated soil. So this is the volumetric behavior that we observed for kaolin clay. By comparing this experiment and providing you the insight and what is happening in the thermal effects of temperature on permeability, intrinsic permeability, hydraulic conductivity of the soil, that part can be as an input to our numerical model, the changes in temperatures, the effects of temperature in the hydraulic conductivity or the conductivity or absolute permeability of the soil. And also we do observe that there's a thermal volumetric changes in kaolin clay, and it's a time dependent. And we observe that there's a thermal contraction in low confine in OCR of 1, and highly overconsolidated soil we observe thermal expansion. But now I'm going to focus on numerical side. So some of those experimental is going to feed our numerical model, and some can be used for validation purposes. So to start with a numerical model, I would like to first start with the coupled hydrothermal loading. So which is, let's forget about mechanical for now, and we see that the coupling that happening when we do have a thermal and hydro response of the soil. And then I will show you the results and our model for a fully coupled thermo-hydro-mechanical model. To show you this, to better basically show that temperature can induce pore water flow even under hydrostatic condition, I'm going to present a very classical problem. It's a cavity problem called, this is a classical cavity problem, specifically more mechanical engineering that works in the porous medium. So this is a cavity problem with a high porosity or high porous medium. We have isothermal, basically no thermal loading and the right and top of the boundary, and the left and bottom part we have a thermal loading. At the bottom we keep the T as a higher load, and then the loading, thermal loading, starts from the bottom corner, left corner, and all the way to the top is diminishing. So TH all to T naught, and then fixing to a constant temperature at the top and right. We have this is we have the gravity, and this is just a high porous medium. If we only consider the heat conduction in the porous medium, as we all know, is the heat conduction is going to be, as we always think that the heat conduction can be the most or the dominant mechanism in the porous medium. If we do consider this heat conduction, this is what we observe. So we developed a numerical model in our group, and we just observe, okay, this is just going to be by only considering heat conduction. That I'm showing the contour. So it's a 1, meaning that the T is equal TH, 0 means that T is equal T naught. So it's a normalized, basically temperature, normalized contours. And we expect that, okay, this is 1, 1, 2, 0, and that's how the contours are. We expected that's a regular conduction is happening. But if we would like to explore the fully coupled thermo-hydro model or hydrothermal model, what are the equations we will need to solve? Is that the first, of course, is the energy equations. That's the changes in temperature, because of this is the term of the convection happening. U is the groundwater flow. When it's a hydrostatic condition, it can be initially 0. And then this is a conduction term. Then we have, of course, the continuity equation, Darcy law. But in Darcy law, what we also need considering is that the force term, because of this gravity, although if we don't have a change in the gravity or the force term, this can be canceled out. But because the density of the water is temperature dependent, and based on this Boussinesq's approximation, the density of the water is depends on the beta, which is volumetric coefficient of thermal expansion of the water, and delta T, or a raise in temperature or cooling in temperature of the water. So if we consider the changes in density of the water, and we insert this into the force term, and then we'll have some, this will generate some velocity, and by changing this groundwater velocity, we expected to see the change difference this U is generating, and by having different U, we'll expect to see different temperature. Again, if you have different temperature, you have different response in the density of the water. So that's actually how it couples the system. And we developed this model, with this fully coupled thermo-hydro system. And the right side, I'm showing you results, again, the normalized isothermal, and we clearly see that either in the hydrostatic condition, this is a vortex happening underground, this is or the cavity problem, and this curved dash blue is showing you the direction of the water flow in the soil medium, in the porous medium. This is an exaggerated, because this is going to be high porous system that we don't have in the ground, but this is just proving that in the porous medium, depending on the porosity, depending on how much is the permeability, we may expect to see thermally induced pore water flow. So after proving this, after showing that this is happening, now we would like to explore this behavior for energy pile applications of, for example, energy piles in the ground, or geothermal energy in the system, or any energy geostructure that we have in the ground. And if we would like to see a soil thermal response close to this heat source in the ground, we modeled the 25-meter pile, energy pile, and we did use of course, this is a axisymmetric conditions, and we modeled the axisymmetric boundary conditions and exploring different intrinsic permeability or different permeability of the medium from very fine to the coarse soil. Do we expect to see this behavior in the ground condition? I'm showing you the results for two different absolute permeability from 10 power minus 10 and to 5 times 10 power minus 3, from coarse sand to fine sand or silt. As you can see here, this is the heat source, and this is the heat source, and the arrow shows the direction of the water flow or induced pore water flow because of the temperature. If we looking at for a high permeable soil, we observe higher groundwater flow or induced pore water flow in the soil in our medium, and this is way higher than if we compare it with the low permeable soil. So that's the reason I will see that if we have higher permeable in the medium, there is a generated pore water flow or induced pore water flow that is towards the heater, and it's going to accumulate in the heat close to the heat source. And this is going to be less and less because of the velocity of the induced pore water velocity is going to be less and less by decreasing the permeability of the soil medium. I'm showing you this as a temperature versus radial distance, and for different permeability, by decreasing the permeability, as we can see, by reaching to the 5, 10 power 10 power minus 12 and 10 power minus 13, almost more than that, anything we have low permeable than that value, we don't see any changes in temperature, or we don't see any changes in the soil thermal response in the medium, in our soil medium. And the reason is that when we decreasing the permeability, therefore the effects of thermal induced pore water flow will be negligible compared to a heat conduction. And that is where the heat conduction is going to be dominant. But when we have a higher permeable soil, the thermal induced pore water flow can make these effects that would be more significant, and heat convection is happening because of this thermal induced pore water flow can also play a role in heat transfer mechanism. By looking at this fluid velocity, which is, of course, it was hydrostatic condition at the beginning as a 0 fluid velocity, but the fluid velocity that you see in this figure is just because of the thermal loading, and it's from radial distance from the heater. And as we can see, by decreasing the permeability, we decreasing with order of magnitudes of the fluid velocity, and which this fluid velocity doesn't have any effect on, or has a negligible effect on, the thermal response of the medium. I'm showing these figures as a kind of from very low permeable to a high permeable zone, from to the left, which is high permeable, to the right, low permeable medium, and changing 1 order of magnitude each. And you can see how that will change the thermal response. I'm using the same temperature contour from 15 degree to 50 degrees centigrade. The heat source temperature is 50 degrees centigrade. And as we can see how the thermal response or thermal propagation is changes with different Permeability because of the effects of thermally induced pore water flow in the medium. Now, after we see this is happening in thermally hydrothermal modeling, and I'm going to now move to our next or the last modeling part, which is the thermo-hydro-mechanical modeling. And that part, that is now you could see that the reason why we have classified in low permeable and high permeable zone. In low permeable zone, there's no thermal induced pore water flow effect. Thus, we need to look at different scenarios, like as thermal polarization. But in high permeable, pore water pressure dissipates fast. But what we do see is a circulation of the water into the soil. So that's why I classified this in two categories. When we have a fine soil, like as a clay soil, when we have a thermal loading, we expected that, okay, the thermal induced pore water flow is negligible. Has a negligible role, but how about the other, like as a thermal polarization, any thermal volumetric changes may happen. To do that, to explore that, basically, we developed a fully coupled thermo-hydro-mechanical model. At the beginning, I'm now first showing you we first developed Thermo-poro-elastic model. We just developed a simple considered model of the Thermo-poro-elastic model to observe this behavior, and then we further investigate the effects of this plastic strain or the advanced considered models. After we developing a thermo-hydro-mechanical model, we have to validate our model. We did use the results of the experiment, Atlas experiment, performed in Belgium. That was this experiment has taken several years, I would say many years, and the results that I do show you here because it's for at least for a couple of years. What happened is that you're looking for embedding the heat source in the ground. Vase pools are, for example, they have the boreholes and then some galleries under the ground, and within this gallery they have some horizontal galleries that was embedded. The heat source was embedded in one of the galleries that I'm showing here. This is the main gallery, and the perpendicular to that we have a heat source, and then at different distances from this heat source there is measurement boreholes to measure the temperature, pore water pressures, and the total stress or stresses. So as you can see, this is the vertical and that's the horizontal. So this is the directions of the heater, and so we modeled surrounding or around this heat source. So we did develop an axisymmetric model around the heater, and we expected that this is deep into the soil, and we assume this is going to be axisymmetric conditions, and for the area that we are focusing on, and we have this heater, and this is measurement borehole. We did consider the changes in the porous medium properties, like as a water properties and with temperature, how that's very important, viscosity or other properties of the soil and water dependent with temperature. And we are developing, that's a thermo-hydro-mechanical model, which we are solving a fluid mass balance, solid mass equation, soil equilibrium equation, and energy equations combined and simultaneously solving. And we have the heat source, heating load at the heat source. For this specific experiment, which as you can see, it took actually 5.5 years, 6 years. So there was a heating load of 3 years, another or second heating load which took 1 year, and then cooling the system, and then they track the performance of the system for 1 or 2 years more after the cooling load. I'm comparing the results that we have for our thermo-poro-elastic model. On the left side, I'm showing the thermal variations, temperature variation versus time, and the blue line is this study, which is a thermo-poro-elastic. Black dashed line is the experiment, and the red one is the François et al. 2009 that they used Thermo-poro-elastoplastic model. For temperature, there is no hassle, so all of these models can capture the thermal response because mostly in this kind of conditions, heat conduction is dominating mechanism. But when we look at the pore water pressure variations or thermal polarization inside the soil, is the thermal pore water pressure variations over time. Again, blue is our numerical model and dashed line is experiment. We can say that during the first heating cycles, we have some error, but acceptable. But in the second heating and the cooling specifically, we have a better capturing the results in the experimental performance. But when we look at the radial or total stress variations, because we're using a Thermo-poro-elastic considered model, and we're just comparing with the stress, and we do see, okay, our model is not capturing well enough the experiment. But when we compare with the Thermo-poro-elastoplastic model that the François had, they haven't either captured as performance. The differences between our model and the François et al., which I'm showing here, is that our model is a thermo-poro-elastic, their model is more advanced as a poro-elastoplastic model. But on the other side, we consider as a fluid properties because of the first part of the presentation, I showed you that the fluid, for example, water properties is highly dependent on temperatures. So in our model, we consider every parameter is a temperature dependent. And because of that, we could either better predict the stresses rather than the advanced model, while our model was a simpler considered model, but because we are considering the high variations of temperature, variation of the fluid properties with temperature. Now I am showing our advanced model, which is a Thermo-poro-elastoplastic model. And this is a same setup, but different heat source, and with the same Atlas experiment, but different heat, different other locations and other type of heating, cooling loads. So we have 1898 and 1897. These are the different galleries they had. So we have, again, heat source, and then two different measurements at different distances from the heater. And this is the gray shaded plane is the axisymmetric domain that we did model. So basically, it's just axisymmetric around that heat source. We developed a fully coupled thermo-hydro-mechanical modeling, considering every mechanism that can happen in the medium. And we, of course, we consider this as a thermo-poro-elastoplastic model. This is developed by Louis et al. And Louis and his students in his group. And this is the model. Basically, we can call it as a modified CAM clay, which is the yield function, the Volumetric yield limit, and also this a slope of the critical state line is a function of the temperature. And we basically use this constitutive model. And we developed 5 different models, from the elastic model with a constant water or constant fluid and porous medium temperature. Basically, model 1 is basically is going to be independent of the temperature. Soil and fluid properties is independent of temperature. It's constant. Model 2 is the elastic model, same as before, but considering it's variable properties, which is temperature dependent. Model 3 is a plastic model. 4 and 5 are again elastic and plastic, but with considering all the mechanism that's happening in the medium, like as chemosmosis, thermosmosis that happening in the medium. And this time we have 3 different heating loading and then cooling cycles. If we look at temperature distribution, and this is the temperature variation with different time, and we expect, and we do see all the models generated and accurately predict the temperature response in the medium. But when we look at the pore water pressure generation and dissipation, or pore water pressure variations with time, we see that all models except model 1, which considered a constant fluid properties, like as a constant volumetric expansion of the water or viscosity of the water with temperature, that couldn't capture the experiment. All the models can capture good enough the pore water pressure distribution. But so you can see model 1, 2, 3, 4, and 4 and 5 also predicted good with a good accuracy the pore water pressure. But as you remember, last time we had difficulties to capture the thermal stress in the medium. This time we have a Thermo-poro-elastoplastic model with considering all the mechanisms in the medium. And as we can see here now, we can capture the thermal total stress variation in the medium with experimental result. Now I'm comparing, and I'm just sharing a few slides at the end of my presentation to show you the volumetric strain happening, elastic, plastic, and thermal strain that is occurring in the medium because of this thermal loading. This is the volumetric elastic strain versus time. It's almost 3 years. And initially we have a heating load. So initially we observed that during all these 3 heating load, we have high elastic strain, but this is negative, and negative here is meaning that this is an expansion system. Then we see some expansion, and then when the cooling starts, we do see the contraction started. And at the right side, I'm showing the volumetric strain. Volumetric, of course, when we are heating, initially we have some dilation or thermal expansion, and then when the temperature stabilizes or the cooling down, we get back to the initial condition. But this figure shows a plastic strain, volumetric plastic strain that can happen in the soil medium close to the heat source. This during the first heating period, we didn't see any plastic strain, and these are at different locations. So it's a plastic strain versus time, and at different locations from 0.5 meter from the heat source all the way to the 2 meter from the heat source. Very closer to the heat source, the plastic strains started to appear faster. And there's of course a lag in the further zones close to the heater, but this plastics starts when the cooling load started, or when the pore water pressure started to dissipate. And we do see the increasing in the plastic strain and during the cooling period. Now we look at those are from the heat source at different signal point. Now I'm showing you temperature variation with the radial distance and pore water pressure variation with radial distance from the heater. So remember, the heater is here, and this is further from the heat source. Of course, during the heating period, black is the first heating, red is at the end of second heating load, and the green at the end of third heating load, and the blue is at the end of cooling. So that's how the temperature increased, and then the temperature cooled down because we are turning off the heater. Now we look at the pore water pressure variations, or thermal generation and dissipation of the pore water pressure, and we could see that at the end of heating, and dashed line, which you can see, for example, here is for the elastoplastic model, solid line is the elastic model. We see higher generation of pore water pressure close to the heat source. Of course, the maximum is at the end of the heating load. And then when we cool the system, we have some drop in pore water pressure, and we see some changes in pore water pressure, and there is a slight changes in the generation and dissipation of pore water pressure with elastic and elastoplastic model, or elastic poroelastic and poroelastoplastic model. Now I'm showing you, we had temperature, pore water pressure. In this two figure, I'm showing you the total stress variation and porosity variation. So that is volumetric changes, basically. If you look at the total stress variation with the radial distance from the heater, this is where we do see higher difference between thermo-poroelastic model and thermo-poro-elastoplastic model. The plastic model, if you look at the end of the cooling, what we observe is that we observe the permanent or the plastic strain because of this heating, cooling happening in the ground. And by heating, we have some increase in the stress, and then we have some changes in the total stress by the cooling down. And if looking at the right side, which is, as I said, is a volumetric or porosity changes with the heat source, at the end of this cooling, we do see some permanent changes in the plastic strain happening at the end of the cooling phase. And my last slide here is to show you the changes in volumetric plastic strain and comparing two scenarios. Both are thermo-poro-elastoplastic model. One, we consider constant fluid properties, like as the constant thermal volume expansion. The other one is a variable thermal volume expansion of the water. So just a simple considering that the variable properties of the water could change the amount of plastic strain that is happening or measuring inside the medium. So this is side by side thermoplastic strain. This is for the first model, which has one at the end of 1 year, at the end of first heating, at the end of the second heating, after 4.5 years and 6 years. Same, but as you can see, we do observe higher plastic strain for when we consider the variable thermal expansion coefficients. To wrap up the presentation and share with you some of our observation and conclusion we had so far, is that for this presentation is the effects of heat transfer mechanism is different in high permeable soil and low permeable soil. And that's why we have to consider it as two different categories whenever we would like to analyze the thermal response of the soil. We observed that intrinsic permeability of the sandy soil can be changed with heating, and we saw a dropping of 40% in soil intrinsic permeability, in sandy soil permeability, when the temperature raised from 20 to 80 degrees centigrade. We do observe that thermal induced pore water flow has a high or a significant effect in heat transfer mechanism in sandy soil, coarse sand, while it does have negligible effect in low permeable, like as fine sand or sills or clay. But on the other side, in clay soils and low permeable soil, when we have a thermal loading, we will have a thermal pore water pressure or thermal polarization, which is further changes the hydraulic response and mechanical response of the soil. And we observe that thermal properties of the saturating fluid and intrinsic properties of the medium have a great influence on thermal polarization. With that, and I would like to use this opportunity to first thank Dr. Reddy for providing and inviting me and providing the opportunity for me to present my result. I would like to thank my students and my current and past students, and also I would like to acknowledge the support for this specific work, which is from the National Science Foundation of the United States. And thank you all for attending this webinar. I would be happy to answer your questions.
Very good, Omid. Excellent presentation. Fascinating.
Thank you for
very, very, very